Okay, so we are going to be spending time talking about pipelining today, and this is broken down into three parts. So we will be focusing on part one of the pipelining lectures. Before we get into the lecture material, I want to talk a little bit about exam one that was conducted, and that's right. So the statistics for exam one are being shown on your screen right now. The average on the exam, a pretty healthy 87. Um, a few students got the full score 101. The lowest score is over a 50 mark. So nothing to panic about, but still there is some room for improvement. About 14 students got above a 91, 8 between 81 and 91, and so on. All in all, I think that you guys did pretty good. Most of the points that were lost were about the fill in the blank multiple choice questions. But in the free response questions, you guys did pretty well. Now going forward, people who are up over here above the 80 mark can try to retain your scores at a high level. But for the people who are in the 50 to 70 mark, I would recommend that they try to push their scores up. Exam solutions have been posted on Piazza under the exam one section. No problem. All right, so let's talk about regrades, right? So for regrades, you can take until the next class day. Regrades by email. My email address is written here. Please explain the reason for the regrade request, and if you can send me that email before next class, due before next class day, which is March 11th. All right, so all in all, pretty good news. A very healthy average. I think the last time I taught CANOS, the average for exam one was maybe low 70s. So that's a 17-point improvement. All right. Any questions or concerns here? Okay, let's get back into pipelining. So I don't want you guys to be looking at your exams right now because this lecture is pretty important material, and it is connected to the next three very closely, and it's very interesting topic. So leave your exams and leave grade scope by the side right now, and I hope that you focus on the lecture material here. All right. See, there is a reason I know that can happen, because I imagine myself doing that. So that's why I said, you can do that later. Just let's come back to this right now. You can go back to that after the lecture is done. Okay. So we'll start talking about pipelining with a very simple real world scenario. So suppose 4 people, Alice, Bob, Kathy, and Don. Their initials are, the starting letter is A, B, C, and D. They are doing laundry, and they're doing laundry on the same day. And they're trying to use a washer, a dryer, a folder, and a stasher. Each of these tasks, washer takes 30 minutes, dryer takes 30 minutes, folder takes 30 minutes, and the stasher, which is responsible to put clothes in a drawer, also takes 30 minutes. So each task takes 30 minutes, and 4 people want to use these available 4 resources to get laundry done. They could do it in a non-pipelined fashion, or they could do it in a smarter, more elegant, pipelined fashion. Let us see what is there to gain. So if they do sequential laundry, meaning one after the other, then Alice takes the first 2 hours, 30 minutes each for washer, dryer, stasher, folder, and all that. Then Bob does it, then C does it, then D does it. 2 hours each. So if they start at 6 p.m. in the evening, they would be done after 8 hours, 2 a.m. in the morning. So A goes first, then B, then C, then D, right? So that takes 8 hours for 4 loads. Obviously, there should be a way to do better, right? So 8 hours is too long of a time. And one thing that is that this sequential laundry scheme is missing is that the washer, for example, goes unused between 6:30 and close to about 8 o'clock, right? It goes unused. That resource is not being used for good 1.5 hours. The same thing applies for the other 3 resources. So can we do something in parallel to reduce our overall time? That is going to be possible with a pipelined mechanism. So this is your pipelined laundry. As soon as A gets done with the washer, B takes it up. As soon as A gets done with the dryer, B uses that resource. As soon as B gets done with the washer, C starts using that resource, and so on. So now things are happening in parallel for the same amount of 2 hours, right? So each person, A, B, C, or D, is using the resources for the same total time, which is 2 hours long, but they are doing things in parallel, which means they are reducing the overall time they are going to be doing laundry. So if they start at the same time, 6 p.m., now they are getting done at 9:30 p.m. So that's a pretty significant gain. Let's take a look at some numbers. This scheme, the pipelined scheme, takes them 3.5 hours to do the same 4 loads. Also note that the time taken for each task did not change. It's still 30 minutes. But if you compare this with the sequential laundry, there is better than 2 times improvement in terms of time taken overall. So clearly, this is something that we can learn from and try to adopt this pipelined mechanism into our computer architecture, into our data path. Because in our data path, there are 5 stages. There is an instruction fetch, there is execute, there is memory access, there is write back. So there are several stages, and if we adapt this mechanism, we may be able to execute instructions in parallel. That's the goal. Some observations. The first observation, like I pointed out, is pipelining doesn't reduce time for a single task. So still washer is taking 30 minutes, still the stasher is taking 30 minutes, and so on, right? So each task, it's still 30 minutes. We didn't change that. But what pipelining does is it raises the throughput of the entire workload, meaning how many jobs get done in a given amount of time. That has gone up. Multiple tasks are operating simultaneously using different resources. So all the tasks are able to make progress at the same time in parallel. What is the ideal speed up? Well, ideal speed up, which is essentially a ratio of time taken to do it in a sequential manner to the time taken to do it in the pipelined manner. That ratio is called speed up. And the ideal speed up would be equal to the number of stages, the number of steps. So in this case, how many steps do we have? Well, we have washer, dryer, stasher, folder, and stasher, right? So there are 4 stages. So the ideal speed up, ideal, would be 4. Let's try to talk a little bit more about the ideal speed up when we get to, we'll try to parse this a little bit more. So I'll prove this. Right now it might not be very obvious, but we'll try to look at it in a little bit more detail. So, other things to worry about. Time it takes to fill the pipeline and time it takes to drain the pipeline, it actually reduces the speed up. If you notice, in the first 30 minutes, only the washer is being used. The other 3 resources are not being used. Right? So it's not like all the resources are being utilized all the time. We are trying to do the best we can. So there would be some reduction in speed up or this parallelism because of filling the pipeline and draining the pipeline. Unbalanced length of stages reduces the speed up, which essentially means that if one of the tasks was taking a long time compared to others, then that would be the bottleneck. That would slow things down. If you have unbalanced lengths of tasks, in this case we had 30 minutes each, so it was pretty okay because everything was synchronized. One thing ends, the other thing starts. The other thing ends, the third thing starts. But if you have unbalanced length, then it actually reduces speed up. Also, the slowest task, so the slowest resource, the slowest stage will actually be limiting your overall rate. Let's now talk a little bit about this speed up. I claimed that the speed up is equal to the number of stages. So for our example, it should be 4. Let's try to see where that is coming from with a speed up analysis that I did in MATLAB, just to demonstrate that number 4. So what I did was, on the x-axis, I have the number of loads, right? In our example, in our laundry example, we had A, B, C, and D. So people were doing 4 loads. But what if I increase that to 100 loads or 200 loads all the way to 500 loads? What would the time taken look like for the non-pipelined version or the sequential version versus the pipelined version? So I have 2 blue lines corresponding to this particular y-axis, which monitors the total time in hours. So if you have, say, 100 loads, then you are taking about 200 hours in the non-pipelined scheme. But for the same 100 loads, you are simply taking about 50 hours in the pipelined version. Speed up is computed by dividing 200 to 50, which gives you very close to the red line here, for which the y-axis is on the right, which is speed up. As you can see, as you increase the number of loads, your speed up will eventually converge at 4, which is the number of stages. We had 4 stages, right? Washer, dryer, and so on. So it would converge to 4 when the number of loads increases. Now, why is this important? Well, it is important because in your data path, when you're trying to execute instructions, you are not going to be executing instructions 4 at a time. Your instructions will keep coming in and they will keep getting executed, right? So you need to look at the speed analysis from a continuation perspective. What if this goes on forever? What would be the speed up? So the red line is actually monitoring the speed up, and it starts off slow, goes to 2, 3, 4, and then 4 is where it converges. But for that to happen, for you to actually see that speed up, your number of loads would have to be significant enough. If you're curious and you want to play with this speed up analysis example, I am providing you with a MATLAB code that I used to generate that plot, to find the total time non-pipeline, to find the total time in hours for the pipeline version. And a lot of the commands over here are just for the sketching purposes, the plotting purposes. So if you're curious and you want to play a little bit more with these, you can do that. So all I did was I swept the number of loads from 1 to 500. I kept 4 tasks per load. Each task was 30 minutes, and I computed the speed up, total time for pipeline, total time for non-pipeline, and I plotted them together. Okay, so I hope that gives you a sort of a validation to that statement. The ideal speed up is the number of stages. Now, there is another way of looking at the speed up, which is, suppose I wanted to get to that number 4. There's another way of doing it. If I asked you guys over here, each load completes in how much? Completes every blank. What would you guys say? Each load. So A is doing a load, B is doing a load, C is doing a load, and 3 is, right. Every 30 minutes you have somebody finishing, right? Every 30 minutes you have somebody finishing. All right, so that would be 30 minutes. And if I ask the same question over here, what would you guys say in the non-pipelined version? 2 hours, right? So the ratio, the speed up, if you want to make that calculation independent of the number of loads, what you are essentially dividing is the time it takes for every load to complete in sequential, which is 2 hours, divided by time it takes to complete in the pipeline version, which is 30 minutes. That would give you that 4, right? All right, we did this, we talked about that, we talked about some speed up, we talked about the MATLAB code. All right, now let's take this laundry example and apply that to instructions and the MIPS ISA. So we have pipelining computer instructions. What we are going to do is we are going to recall the amount of time an instruction spends in each step. So for example, in the last lecture, we were talking about instruction fetch taking about 2 nanoseconds, register access 1 nanosecond, ALU and adder 2 nanoseconds, data access in the memory 2 nanoseconds. So we are going to use these to indicate the time it takes for every step. The example that we are going to follow here is 3 load word instructions. So what are we doing here? We are taking the base address at 0, adding an offset of 100, and we are loading something that is present at that target address into register 1, into register 2, into register 3, right? So 3 different memory locations, right? These are 3 different memory locations, the contents of which are getting loaded into 3 different MIPS registers in the register file. So let's try to look at how the instruction can be laid out as a function of time when you do the pipelining versus when you don't do the pipelining. So right now, can you guys tell me whether this is a pipelined structure or not non-pipelined structure? You see, one after the other, right? So clearly this is a non-pipelined, exactly right. It's the sequential, one after the other, the slow method, right? So Your x-axis right now is time in nanoseconds. Should be there. Time in nanoseconds. And your y-axis over here is program execution order, right? So you have load word, first one, second one, third one. Those are instructions over there. So the first load word instruction uses all the 5 stages: instruction fetch, register access, ALU, data access, because you need to read the memory, then register, because you need to write into the register file. All 5 stages are being used. And if you add up the time taken by each of these stages, 2 nanoseconds here, 1 nanosecond there, 2 nanoseconds there, 2 nanoseconds there, 1 nanosecond there, you would get 8 nanoseconds. So you go 8 nanoseconds for the first one, 8 nanoseconds for the second one, and 8 nanoseconds for the third one, giving you a total non-pipeline time of 24 nanoseconds. Sure, we can do better than this, because while your instruction fetch stage is going on over here, after it gets done, we can start using that particular hardware, that particular resource, to start loading things for the next instruction, right? Why wait until 8 nanoseconds? I can start using that instruction memory right away. So if you do that, at the top here, it is the same analysis that we did for the non-pipeline one. At the bottom one, we have the pipelined version. Now, one thing to note over here is we are essentially reading and writing to the register file at different times. So for example, when you are, what are you doing over here? Are you reading or writing? With respect to the register file, are you reading there or writing there? Reading, right? Because at the beginning you read, then you perform the execution, then you will write back. So register access, for the first time, you are reading there. And then at the very end, what are you doing here? Writing. Yes. Why are you writing over there? Because load word instruction means take something from memory and write to the register 1, right? So you are writing eventually. So the way we are going to distinguish between read access to the register file and write access to the register file is we are going to read in the second half of the 2 nanosecond time period, and we are going to write in the first half of the 2 nanosecond time period. Now, the next question is, why do you want to make this 2 nanoseconds? The reason is we have to wait for that anyway. If you make that window of register access 2 nanoseconds, everything becomes 2 nanoseconds, and now things are uniform. Each step is taking the same amount of time. So that will benefit us in terms of speed up, right? So I'm going to be doing register reading in the second half of the 2 nanosecond cycle and register writing in the first half of the 2 nanosecond cycle. So that's something to note. Next. All right. So you're done with the instruction fetch step. As soon as you're done with that, start using the same resource, the same hardware for something else. In this case, the second instruction and then the third instruction. So you're not waiting for the first instruction to finish. You are instantly, as soon as it's done, you jump to the next instruction. Do you know what the pipeline time would be if you didn't extend it to 2 nanoseconds? So here, it has to be extended to make the boundaries coincide, because this is going to tie back to the fact that we need to worry about, in order for the pipelining to work, we need to do a lot of storing of intermediate values, intermediate control signals. So the 1 nanosecond over here that we are giving up actually is negligible when it comes to maintaining the pipeline registers, because later on what we'll do is we'll be adding buffer registers between each stage, because there are lots of problems we could end up if you just move this, start using this. There will be some serious consequences. So I'll touch all those topics as we go on. Now we have got this. What is the pipelined time now? It started over here, it ended at 13 nanoseconds. So the pipelined time is 13 nanoseconds versus 24 nanoseconds. So I hope we have the non-pipelined, we have the pipeline, we can start computing the speed up. Speed up is essentially the time taken to complete without pipelining divided by the time taken to complete with pipelining. So in our example, we had 24 nanoseconds for the numerator, 13 nanoseconds for the denominator. We got a speed up of 1.8. And if you were running pipelining at full blast, meaning one instruction after the other, and so on, right? Continuous, then we would get an instruction completes in every 2 nanoseconds, right? You see this? This guy ends at 9 nanoseconds, 13 nanoseconds. This is 9, this is 11, this is 13. So every 2 nanoseconds, you have an instruction finishing. The average or the long-term speed up is the time it takes for every instruction to complete without pipelining divided by the time it takes for every instruction to finish with pipelining, right? So over here, things get done every 8 nanoseconds. One instruction finishes in every 8 nanoseconds. In the pipelined version, every instruction finishes every 2 nanoseconds. So if you divide those two to look at the full blast, running at full blast, meaning one after the other, the same thing that we did for 500 loads, right? So if you increase the number of instructions, what would it tend to? The average speed up would tend to 4. Okay, so that's good. So there is a factor of 4 improvement when you start looking at pipelining. However, we also said that our ideal speed up is equal to the number of stages. In this case, we have 5 stages: fetch, register access, ALU, data access, register access. So there are 5 stages over here. So we should have been looking at 5 as the ideal speed up number. However, our speed up number worked out to be 4. Why is that? The answer to that is because of that 1 nanosecond missing bit in the register access times. In fact, our total time for the pipeline instruction is not 8 nanoseconds, it is actually 10 nanoseconds. So if you look at this, you have your instruction fetch, then there is a wastage of 1 nanosecond here, which is used to synchronize all the instructions. And there is another wastage over here while you are doing the writing. So if you look at the total time, then it is a total of 10 nanoseconds. So in fact, it is not 8 nanoseconds divided by 2 nanoseconds. It is 10 nanoseconds divided by 2 nanoseconds. It would have been 5, but we are getting 4 because of that loss. So each pipelined instruction really takes 10 nanoseconds, which is why our speed up is not showing up as 5, but it is showing up as 4 because of that loss. Some characteristics of pipelining. The performance benefit. While the time for executing instructions is the same or even more, right? We actually increase the time of register access in order to synchronize instructions. So even though there is no real benefit in the time it takes for each step, if you look at the overall execution time, it has decreased. by the factor of speed up. You're ideally looking at one instruction to finish every clock cycle. So IPC, instruction per clock cycle, is still 1, right? We looked at the clock rate has to be the inverse of the clock cycle time. So you're still looking at one instruction finishing in one clock cycle. The pipelining is transparent to the programmers. The programmers only worry about writing the instructions and them getting the results of their instructions as soon as possible. They do not really directly care about whether it is being pipelined or not. But as computer architects, we can give them the results faster by employing this parallelism technique through pipelining. So parallelism is achieved over here. It utilizes almost all the data path elements at every stage, but it is for different instructions, right? So if you look at this, the instruction fetch stage was using some hardware for instruction 1. Then as soon as it got done, the second instruction was using that hardware. The third instruction was using that hardware. So nobody is like idle. Everybody is working almost all the time. All right, talked about this, we talked about this, we talked about this. All right, now let's talk about our MIPS instructions. Because like I said, we have to be a little bit careful about using the hardware parallelly, because there is a consequence, right? Because every stage gives you certain values. And if it gives you certain values, you cannot just overwrite it with the results of a new instruction coming in, right? You would have to preserve them so as long as they are absolutely needed to complete that instruction. So you have to store them temporarily in interstage pipeline registers. We'll take a look at that. So MIPS instruction set is designed with pipelining in mind. All the instructions are fixed length. There are only a few formats, so as common as possible. Memory operands only appear in the load or store instructions. Operands are aligned in memory. Instructions are also aligned in memory. So pipelining, which takes, the advantage there is if things are aligned, if things are of the same length, then things can be made parallel. And you can really take advantage of that. And MIPS supports that because it was designed with that in mind, with pipelining in mind. A few challenges, and this will essentially indicate why we actually need those interstage pipeline buffers. The first problem that we will look at is called data hazard. Sometimes the next instruction you want to put into your pipeline cannot execute in the next clock cycle. For example, think about these two instructions back to back. There is an add instruction immediately followed by a subtract instruction. What are you doing here? You are taking the contents of this guy and this guy, and you are adding them. And you are putting the result into S0. But if I immediately use S0 as an operand in the next instruction, I may have problem. Why? Does this S0 have the result of this addition, or is it before the addition was done? If you wanted this to be using the result here, then you may or may not have finished that add instruction. So you are in trouble. Take a look at this timing diagram here to understand more. When are you really writing to S0? You're writing to S0 over here, right? Write to S0 is happening way over there. But if you started your subtract instruction, which is the next instruction, you need the new value here. Need new value of $S0 here much earlier. So it's not going to have that, right? It's actually going to have a old value of S0. That's what is going to be used here. Because in one case, S0 is the destination, and in the other case, S0 is an operand. Now let me ask you guys this. If these two instructions were reversed, would it be a problem? Would it lead to a data hazard situation? It would not lead to a data hazard situation, but clearly it would not lead to what the designer is trying to achieve with their instructions, right? So it's not going to give them the exact application, whatever they are trying to do with that instruction, but it will definitely not be a data hazard situation, because in that case, the dependence is not there. But if there is a dependence like this, that situation is called a data hazard. You cannot write to a register and use it immediately in the next register without having this problem. There are some solutions. We'll talk about the solutions later. So this is one challenge. The second challenge is with respect to branching. Again, the same situation. The next instruction cannot execute in the next clock cycle. The example over here is a branching instruction. Branch when these two are equal, right? You check 1, you check 2, you check the contents of 1 and 2. If they are equal, then you branch to this new location. This plus PC plus 4 and all that, right? This is in words. And the next instruction is an add instruction. It is not depending on this branch instruction. However, if we actually put this into the pipeline, you have started executing it. But did you really intend to? I don't know. I don't have the results of the branch condition yet. I have not checked whether this equals that or not. So how can I work on the add instruction, which is only satisfied when this is actually not equal, right? So you are actually attempting to execute an instruction which may not be necessary, right? Because the branch, you don't know whether the branching goes to a new address or the next address. You don't know that yet. That kind of a challenge is called control hazard. Again, there are fixes to this, and we'll talk about that. What would be a very obvious fix to this? Can you guys think of an obvious fix to this? Oh no, not pipeline is never an option. Not anymore. Delay add until ALU is done for BEQ. Okay, not doing instruction yet. Okay, if the instruction fetch is then delay. Actually, do both. Just don't take the branch. Okay, here. Pick one, right? Pick one and start executing. If you fail, you can always retrack. So depending on the probability of the branch being taken versus the branch being not taken, you either start executing the next instruction or you start executing the new instruction, but start working on it. Because if you start working on it, then you have made some progress, which you can later give up on without any issue. You are anyways not having that gain to begin with, right? So you start working on something, and then you can deal with the repercussions later. If you want to, if you have to backtrack, you can backtrack later. So those are some of the ideas that we are exploring in the pipelining, the next two lectures. Let's see. So this is your control hazard. Let's go to the pipelining challenge number 3, which is structural hazard. In this case, you have a load command followed by any three commands. So you have a load command here in which you are trying to do some data access, right? You are trying to do a memory read over here. And you have three instructions after that load word. And if you look at the third instruction right here, the time at which load word instruction is trying to read the memory to do data access, it is the same time at which the last instruction in this list is trying to read the memory to instruction fetch. Over here also there is a memory read. Now, if your instruction memory and data memory are separate, then you don't have a problem. However, if they are the same memory, then how are you going to be able to do memory read of two different locations at the same time? Cannot happen, right? Because two different reads require two different addresses you want to be able to read at the same time. So that will be in contention. That is called structural hazard. Again, there are solutions to this. Actually, there are solutions to all the three challenges. Questions about the three challenges? Data hazard, control hazard, structural hazard. This is much more complex than laundry. Yes, it is. But I hope that you guys are seeing that there are going to be patterns, right? Repetitive patterns, right? For every instruction, I have to worry about these things. Fetch, register access, ALU, data access, register write. So there is uniformity to instructions. If we were pipelining, won't the control signal change? Yes, you are absolutely right. Which is why we have to save them. We have to temporarily store all the control signals. You're absolutely right. That's coming up in the next few slides. All right. So let's summarize the three pipeline hazards. One is the data hazard, control hazard, structural hazard. Data hazard was what? Attempt to use an item before it is ready. That is, instructions are depending on the result of the prior instruction still in the pipeline. Can do that. If you do that, then you will actually work off of the value that was there before the instruction was executed. So not the new result, but the old result. The next one is the control hazard, which is to attempt to make a decision before the condition is evaluated, such as what happened in the branch when equal instruction. The third one is structural hazard, which is essentially contention for the same hardware resources at the same time. Some ways to deal with hazards, and we will be looking into at least the first two we will look at in detail, and we'll talk more in the next two sessions on pipelining. The first one is stall, which is essentially using NOPS. NOPS is no operation. What that means is I'm going to execute an instruction which is NOP. No instruction at all, no operation at all. Just so that I can still be doing pipelining without having to deal with the hazard. We'll take a look at examples about this stalling technique in the next lecture. Rearrange code. You can rearrange your MIPS instructions so that you don't end up in one of the three hazard situations, but you just have to be careful that you are actually consistent with the MIPS instructions to get what you wanted to achieve. with the instructions. So rearranging code is a pretty good idea. It just takes a little bit of time to do it. There are hardware tricks to do it, which we are going to be talking about, essentially including, this sounds hard. Yes, it is hard. The hardware tricks are to include the interstage pipeline buffers to store things temporarily until at least you are done with using them. Is the rearrange code managed by the compiler? The more complex compilers can handle that, but if your compiler is a basic compiler, then you the assembler, right? So the assembler, you may need to do that yourself. So it depends on the quality of the assembler. But some assemblers do give you that option to rearrange the code. Let's see, hardware tricks, and then more in the next two sessions on that. Let's take a look at pipelined data path. So everything in pipeline, we have 5 stages, 5 steps: instruction fetch, instruction decode and register fetch, execute, memory access, memory read completion, right? So each of these on the left is the step name, followed by, for R-type instruction or load store or branch or jump, what is happening in terms of registers in each of those steps. For example, if you are doing instruction fetch, for all types of instructions, you are doing things the same. You are taking whatever is in the memory at the location of program counter and putting it into the instruction register. You are also updating the program counter by 4. You are adding PC equals PC plus 4. That's your instruction fetch. While you are doing the instruction decode or the register fetch, you are taking some bits of the instruction register and putting it to the A side of your read register 1, right? So that was if you this is talking about take some bits of the instruction and go into the read register 1, read register 2, and so on. And then when you do the ALU out, which is essentially this guy right here, that's your 32-bit sign extended value of some of the bits in the instruction. So all of that is over here. While you're doing execution, well, it depends now on whether it is a I-type, R-type, whether it's load or store, whether it's branching, or whether it is jumping. So different types of instructions have a different meaning of execution. Then there is memory access. Well, in some of them there is memory access, for some of them there is no memory access, especially for load or store. For load or store, there is memory access. In load, you are reading from memory. In store, you are writing to memory. No memory access for branch, no memory access for jump. In fact, even for the R-type instruction, the memory access is essentially bypassing the memory. Just the ALU output going to the write back stage, right there. Memory read completion is essentially loading the data to the memory data register. Now, this particular diagram will help organize your thoughts when it comes to these 5 steps. There are clear boundaries for each step. Your instruction fetch or IF has these specific resources. There is an adder to compute PC plus 4. There is instruction memory and the program counter. Then there is a mux to select between a new address or the PC plus 4 address. All of that is in the instruction fetch stage. Then there is instruction decode, in which there is a register file and a sign extender. The next is the execute state, in which you have the adder to compute the branch address, the ALU, and also the ALU source MUX. Then there is memory access, in which there is data memory. Then there is a write back stage, in which you are selecting whether you are writing the read value from the memory or you are writing the ALU result to the register file. So these clear 5 steps and their corresponding resources will help us get to a complete pipelined data path. Because all we are going to do is, in the middle, in the middle of each of these, we are going to introduce a buffer, interstage pipeline buffers. We are going to write some intermediate results onto them, and then as we move through these stages, we will be using them and dumping those values. All right, let's move on. There they are. So we are going to put the pipeline registers between each of those stages. So there were 5 stages, right? So let me just box them up. There was this instruction fetch. Then there was the instruction decode stage. Then there was the execute stage. Then there was the memory access stage. And then there was the write back stage. And now in the middle, you are, maybe there are too many lines here. I'll just erase them. Now in the middle, you are introducing these interstage pipeline buffers or pipeline registers. So the interface between instruction fetch and instruction decode. The interface between instruction decode and execute and memory and write back. So for 5 stages, you need 4 pipeline registers in between. What does this hold? IF and ID. Well, it can only hold 2 things that are coming into it, or essentially 2 things that are supposed to be going to the decode stage. PC plus 4 and the value of the instruction register. So those will be put onto the pipeline buffers temporarily. For the IDIX decode / execute pipeline buffer, you have PC plus 4, read data 1, read data 2, and the sign extended value. Next stage, add result, 0 result, ALU result, and the read data 2. Next one, data read from memory, ALU result. That's it. Those are the values that you need to hold temporarily. Let's try to highlight some let's see what it means to write and read these pipeline registers. So let's suppose we are doing a load word instruction and we are trying to show what the instruction fetch stage looks like. So the instruction fetch stage is highlighted in yellow over here. Nothing else is highlighted. So what it does is it computes PC plus 4. So it uses program counter, it uses the adder, and now this guy is ready in terms of its PC plus 4 entry. But that would also be functioning in the instruction fetch step. And now you are reading from the instruction memory. So the right half of the instruction memory is highlighted to indicate that there is a read operation going on. So you read from the instruction memory what? The instruction register, right? The instruction itself. That gets written to the IFID interstage pipeline buffer. So when you see the highlight being on the left side, that indicates that you are writing to this, and when the the highlight is on the right, that means that you are reading from it. So for the instruction fetch stage, the instruction is read from the instruction memory and you compute the PC plus 4 value. What you store on that IFID register is the instruction as well as the PC plus 4 value. And at this point, you might be able to guess what happens as you move along. When you go to the next stage for the same instruction, which is load word, now you are over here, right? So you are using the ID, IFID interstage pipeline, but for reading purposes. You are reading this pipeline buffer, you are going through the register file, you are doing the sign extension, and you are writing to the next interstage pipeline buffer. But it frees up your IF. It frees up the resources in the IF stage so that you can bring in a new instruction over here and write things to the IFID register. Right? You see that they are getting used, the new ones are coming in. So decode instruction and read register file. That was happening as far as the load word in the decode stage was concerned. For load word, you need register 1, contents, and also the sign extended immediate. Okay, so you got read register 1, you got the sign extended value as well. Both will be saved on the IDEX interstage pipeline buffer. So read from this and write to this. And what's in this stage now is your next instruction can start getting in there. And as the load word instruction progresses to the next stage, which is the execute stage, now it is using the ALU. It is reading from the IDEX register and writing to the EXMEM register. The last stage is what? Not the last stage, but the next stage to that is the memory access. You are still using the load word instruction. Read from EX memory, read the data from the memory itself, write to the mem write back interstage pipeline buffer. Finally, you write back. Write back where? You take contents from whatever you read just now and you have got to write back to the register file. But while this is happening, we do not know what that write register is because all that data is lost. If all these values are being stored in buffers, where are the control signals being stored? In the same buffers. We have not just shown them yet. So on top of this, you will need control. Where is that control? Right here. So we just didn't we didn't show it yet. Now, when you are trying to do the write back, you see what happens. When you're trying to write back, you need to know which register to write it back to. Where is that information? Well, that information was part of the instruction, which we have lost, right? So we don't know right now which register to write to, which means we need to even store that information throughout the lifetime of this load instruction. And the way we do that is, let us put that particular instruction, right? That register is part of the instruction, whatever that destination register is. Let us store that into the IDEX stage, store that in the EXMEM stage, store that in the write back stage, and then we can use it at the end. So whatever you need, preserve the destination until the final stage. Not just applies for this case, but whatever you need later on, you have to preserve that. Whether it is a register, or a control signal, you have to preserve that until it is supposed to be used. So in this case, we had to preserve the write register, and we did that by simply writing that information all throughout, right? IDEX, EXMEM, mem write back, and then we were able to use it at the end. Because a new instruction coming in will start overwriting those things, right? That's what we don't want. Now let's talk about control, because it looks like you guys are clearly looking for the location of where to store control signals. And this is where to store the control signals. You have a lot of them. Register write, ALU source, ALU op, register destination, branch, mem write, mem read, memory to register, PC source. All of those were control signals that we have learned about. Now we are going to have to store them so that they are essentially used at the right time. So what I mean by that is, you don't need to store all the control signals at all the times. As soon as their job is done, you can get rid of them. You don't need to save them beyond their purpose. But you have a lot of them to store, and that's exactly where they will be stored, in the pipeline buffers. So let's talk about the control problem. As soon as we have the instruction, we know all the control signals. We know PC source, ALU source, all of that we already know. How? Well, from the instruction goes to the main control unit, right? And as soon as the instruction is available, it gives you all the control lines. So as soon as you have the instruction, you know all your control signals. Some of those control signals are appropriate for decode stage, some for execute stage, some for memory access, some for write back. So not every signal is appropriate for every stage. For example, if you look at this, register write is only used in the decode stage. Do I need to preserve this? You absolutely should preserve this, because at the very end, when you're trying to write, that signal needs to be activated. So you need to preserve that. ALU source, well, once you pick the ALU source, you don't need that beyond that instruction. You can get rid of it, right? So preserve the control signals as long as you need them, no further. All right, so at each stage is working on a different instruction, which is what the problem is. We need a mechanism to ensure that each stage gets the control signals for the correct instruction. But if we try to do a state diagram for this will be very huge. We need an easier way. The easier way is to essentially get organized by grouping the control lines. Let us do one per stage. So for the first one, which is instruction fetch and PC increment stage, that is pretty straightforward. Why? It looks like over there we don't have any control signals to worry about. If you have PC source, just put that on the instruction fetch, instruction decode pipeline buffer. Next, instruction decode and the register fetch stage, which is in the second stage. Again, it's pretty straightforward. We just need to save the values. So that's the stage in which the control unit, because that's the instruction decode, right? So that's the stage in which the control unit finds out all the control signals. You need to put them into the IDEX interstage buffer. Go back. For the execution stage, you need register destination, ALU op, ALU source. Those are the three that you need to save. In the memory stage, you need to save the branch, memory read, memory write. you need that information from before, right? And then for the write back, you need register write, like I pointed out, and also the memory to register. And you can clearly look at some of these, right? Memory to register, and then you have to write it back to this, so you need that. So some of them are pretty obvious. By looking at the thing, you know that those are the controls. But for register write is not very obvious, because it is when you are doing the write at the end. All right, let's move forward. All right, so that's your solution. Go from the instruction, which is going to be stored in the instruction fetch, instruction decode pipeline buffer. Go to the main control unit, compute all your control signals, put them onto the next pipeline stage buffer. WB stands for write back. So there might be certain signals for write back. For example, there is memory to register, there is register write. A few of them for memory access stage, memread, memwrite, and I think it was branch, right? 3 of them. Then a bunch of them for the execute stage, right? ALU source and all that. So the first one, IDEX pipeline buffer, has all of them stored. The next one is what? In the middle, you have execute. So the execute controls are used here. I don't need to save them again. I can dump them and only preserve the write back and the memory related control lines. And then I have the memory, right? Over here I have the memory. So I use up memory, I only need to preserve write back. And at the end, I use write back, right? So as you are progressing through, you are using and then only preserving the ones that you will later need. All right, I think this is it. Pass control lines, sure, yes. So if you add data path with control, with interstage buffers, with all the control lines, that is how it looks like. So you have got the data path with instruction memory, PC, adder, PC source, MUX. The interstage buffers are being highlighted in pink here. On top of that, you have the control lines, which are highlighted in blue here. Rest of them are essentially the data path wiring, and that's it. So things, and if you see this is kind of tying multiple lectures together, right? So it's tying the data path with the control unit with the pipelining content. So it's kind of bringing all those ideas together into one particular block diagram. All right, I think that is it for today's lecture. I'm going to stop recording. You guys can ask me questions here or start working on the activity.